In this question, I'm asking you to complete each of the following reactions by drawing the products. And that you can assume that means to draw the major products, but there's nothing wrong with drawing all the possible products. Right. So in this first one here, this one here with the secondary alcohol using hydrobromic acid, just think about what's happening here. The oxygen is going to pick up that proton. That's going to create a good water leaving group. Now, that leaving group can leave, or the bromide could come in and kick it out via SN2. So we got to think about, what pathway is most likely going to take place here. Being that this is a secondary carbon, so with a leaving group on the secondary carbon, it could do SN1, it could do SN2. So let's evaluate it a little bit further and think about what is likely going to take place here. Right, well, this secondary carbon, it's next to this tertiary carbon. So this would be a branched secondary, meaning there's a lot of sterics on this side of it. And then there's this other carbon over here. Most likely, what's probably going to happen in this case is the leaving group water is going to leave and we're going to end up with a carbocation. Now remember, that carbocation that forms on this carbon is planar, which means when the bromide comes in and attacks, it can do it from either plane of this carbon. What that means is you could get this product here where you have this is still wedged. The bromine could add from the same side as that, in which case you would have the bromine there. So you would have a cis product. Or since that carbocation is planar, here's that wedged methyl group, that bromine can add from the other side, giving you a trans product. So both of those are possible there. In this next example, same secondary alcohol, but we're going to use use this reagent right here. Um, Remember, these reagents, they work via SN2, so we can't even use these reagents on tertiary alcohols. So it's going to work via SN2 here, which means that we're not going to form a carbocation here. We are going to form a good leaving group when the oxygen bonds to the phosphorus. That's going to be our leaving group. One of those bromines gets released, and that acts as a bromide that comes in and attacks us. Now, here's the thing. Remember, SN2 reactions occur via the backside. The nucleophile bromide in this case is going to approach opposite the leaving group here, which means when that bromide comes in, it's going to come in from the same side as that methyl group that's already there. So in this example, the only product you should draw is this cis product right here. In this next example, we have a secondary alcohol with these carbons next to it, which are highly substituted. Well, think about what's going to happen here. The oxygen, again, is going to grab this proton. When it grabs this proton, it creates a good leaving group. Now, remember, this is a secondary carbon, but it's branched, meaning there's a lot of sterics on this side and this side. That's going to decrease the amount of SN2 that is occurring. So what's going to most likely happen here is this water leaving group is going to leave when it's protonated. It'll leave, form a secondary carbocation. Now remember, if there's a potential to make a more stable carbocation, you can assume that will occur. So if we form a secondary carbocation here, what's going to happen is one of these methyl groups is going to shift over. When it shifts over, that is going to cause one of these carbons, wherever the methyl group leaves from, going to cause these carbons to become positively charged, right? That's going to create a tertiary carbocation. So we have the potential to go from a secondary carbocation to a tertiary carbocation. You can assume that's going to occur. That's going to mean that the iodide, when it adds, so here's those two methyl groups. The one that shifted over, I'm now putting there. The one that remains, I'm still putting there. And then the iodide is going to add to that tertiary carbon. And that could have happened at either side. In this last example here, we're using one of those thionyl chlorides. Remember, these work via SN2 as well. These are a great way to replace a hydroxyl group with a chlorine without any concern for rearrangements. So what's going to happen here is we're going to create a good leaving group when the oxygen is bonded to the sulfur. We'll create a good leaving group. That's going to make this carbon here susceptible to nucleophilic attack. The chloride that gets released in the process, it's going to attack that and kick that out. You replace the hydroxyl group directly with the chlorine. So go back into the notes if you want to look at a mechanism for this, but this would be the final product for this one here.